So in previous videos, we've talked about the different categories of base and nucleophile that you could have, and those have implications for the type of mechanisms that are likely to happen. If you have a strong base, that favors an elimination reaction. If you have a strong nucleophile, it favors a substitution reaction. What we want to do is pinpoint the exact type of mechanism in order to figure out what type of product we'll get. And the type of mechanism will depend on two things. The first thing it will depend on is the type of nucleophile and base we have. That we've discussed. The second thing it will depend on is what type of carbon the leaving group is attached to. Remember, all of these substitution and elimination reactions have that leaving group in common. So what type of carbon is the leaving group attached to? Is it attached to a primary carbon? Is the leaving group on a secondary carbon? Or is the leaving group on a tertiary carbon? So those are our three possibilities. Okay. So, in those cases, let's think about all these possibilities one at a time. Well, first of all, we'll deal with this first column, strong base, weak nucleophile. If it's a strong base and a weak nucleophile, already we know that an E2 mechanism, already we know that an elimination is going to happen. So it'll be some type of an E mechanism, either E2 or E1. The base is making the elimination want to happen, and the nucleophile is weak, so it's not going to be able to compete. Okay, but even if you think inside of elimination, will it be E1 or E2? The rate law for an E2 equation is that the rate depends both on the substrate and on the base, because everything happens in a concerted process, so both the substrate and the base are involved. In an E1 reaction, the rate only depends on the concentration of the substrate, because the base is not involved in the rate-limiting step. Well, you could see that if you have a strong base, that's going to speed up. That'll affect the rate of an E2 reaction, but it won't do anything for an E1 reaction. So it'll speed up an E2 reaction, and now the E2 is outcompeting the E1. So, for these strong base weak nucleophiles, no matter what the leaving group is on, you have an E2 mechanism. Because the strong base speeds up the E2 reaction, so it outcompetes the E1. And the fact that you have a weak nucleophile means that the substitution can't compete with elimination. Okay, well, let's think now about a strong base or a strong nucleophile. If you have a strong base, that's going to favor an elimination reaction. If you have a strong nucleophile, that's going to favor a substitution reaction. And so we'll get a mixture of both of these. At least we will if the leaving group is on a primary or a secondary carbon. So if it's on a primary carbon, we will get elimination reactions. We will also get substitution reactions. Now, because the base is strong, a similar thing happens in this case as happened in the previous one. If the base is strong, that really speeds up the E2 mechanism. It doesn't do anything to the E1 mechanism. The base is not in the rate law for that. And so the E2 outcompetes the E1. And the elimination reaction that happens here is an E2 mechanism. Similarly, for an E1 reaction, for an SN1 reaction, SN2 versus SN1, you'll remember that the rate laws for those, the rate law for an SN2 is that the rate depended both on the substrate and on the nucleophile, whereas the rate of an SN1 reaction depended only on the substrate. Well, if we have a strong nucleophile, that is going to speed up the SN2 reaction, but it won't do anything to the SN1. So the SN2 reaction will outcompete the SN1, and with the strong nucleophile, the substitution reaction you get would be an SN2. Now that's true both for a primary carbon and for a secondary carbon. That whole line of reasoning is the same. You get elimination reactions because you have a strong base. But because you have a strong base, it speeds up the E2 mechanism, and that outcompetes the E1, so you get E2. You have a strong nucleophile, so you get substitution. A strong nucleophile speeds up the SN2 reaction, but does nothing for the SN1 reaction, so the SN2 reaction outcompetes, and you get the SN2 product. So you get a mixture of products there. Now in the case of the leaving group being on a primary carbon, if the leaving group is on a primary carbon, then there's plenty of room for the nucleophile to attack. And that favors the SN2 reaction. So here, although you do get both products, your major product is the SN2, and the minor product is the E2. The roles are reversed if the leaving group is on a secondary carbon. If the leaving group is on a secondary carbon, it's harder for the nucleophile to reach it. Remember, the bases that you have in elimination reactions don't have to reach the carbon that the leaving group is on. They have to reach the beta hydrogen. It's easier to reach. And so if the leaving group area is more crowded, it's going to be harder for the nucleophile to come in, and the base, it'll act as a base more often. So in this case, you still get the two products, but now your major product is the E2 product, the elimination product, because there's less crowding for that one. And your minor product is the SN2 product, because there's more crowding. It's preventing the nucleophile from being as effective. Finally, if the leaving group is on a tertiary carbon, you only get the elimination product. And we've seen this before. We've seen in chapter 7 how if the leaving group is on a tertiary carbon, you cannot have an SN2 mechanism. And you might say, yeah, that's true, but in chapter 7 we said that if the leaving group was on a tertiary carbon, you'd get an SN1 mechanism. So why don't we get an SN1 mechanism here? And that's because the base is strong. The SN1 reaction would happen relatively slowly, and the elimination reaction would happen really quickly because this base is strong. And so the elimination reaction outcompetes it. So the base is strong. That means that the E2 mechanism outcompetes the E1 mechanism, as we've seen before, because the base is in the E2 rate law, but not in the E1 rate law. And so if you have a strong base and a strong nucleophile, if the leaving group is on a primary carbon, you'll get E2 and SN2, but mostly SN2. If the leaving group is on a secondary carbon, you'll get E2 and SN2, but mostly E2. And finally, if the leaving group is on a tertiary carbon, the carbon that the leaving group is on is too crowded for the nucleophile to come in and attack. And so the molecule instead acts as a base and snatches up one of the beta hydrogens. And since it's a strong base, it favors E2 over E1. Okay, well, what if you have a weak base and a strong nucleophile? Well, that is going to clearly favor substitution. Now, if the leaving group is on a primary carbon and you're doing substitution, that's going to give you an SN2 product. If the leaving group is on a secondary carbon, well, it's still a choice between SN2 and SN1, but because you have a strong nucleophile, that speeds up the SN2 rate law. It doesn't do anything to the SN1 rate law. The nucleophile isn't in that. If you have a strong nucleophile, it speeds up the SN2 reaction, and the SN2 reaction outcompetes the SN1 reaction. So even though both SN2 and SN1 can happen on a secondary carbon, if the leaving group is on a secondary carbon, because we have a strong nucleophile, that favors the SN2 mechanism. So we would have an SN2 reaction in that case. Now, if the leaving group is on the tertiary carbon, we will still do a substitution because we have a nucleophile here. But as we saw in Chapter 7, if the leaving group is on a tertiary carbon, it's too crowded for the nucleophile to swoop in an SN2 mechanism. The leaving group has to leave first so that you have the trigonal planar molecule, and then the nucleophile can attack. But that is an SN1 mechanism. So if the leaving group is on a tertiary carbon, in that case you'd get the SN1 product because this is just too crowded for the nucleophile to swoop in. All right, finally, what if you have a weak base and a weak nucleophile? In that case, it's hard to get the reaction to happen at all because these are not strong reagents. There's not a big push for them to react even. They're very stable the way that they are. And usually these will happen with the E1 or SN1 mechanisms. That's what we've seen. The E1 mechanism uses this weak base, and the SN1 mechanism uses a weak nucleophile. After all, if the base or the nucleophile were strong, then that would speed up the E2 reaction or the SN2 reaction. So these are really going to be SN1 or E1 reactions with a weak base and a weak nucleophile. Both of those require the creation of carbocations, and carbocations really don't form on primary carbons. They're too unstable. So you end up not really getting products in this case. It's too hard to get the reactions to happen. If a leaving group is on a secondary carbon, it's both hard to get the reaction to happen, although you can get secondary carbocations. They're not the best, but you can get them. But in addition to that, you just form too much of a mess of products. You could get carbocation rearrangements, first of all, in both E1 and SN1 products. And in SN1 reactions, if you have a chiral center, you'll get a racemic mixture. In E1 reactions, you can get the Zaitsev and the Hoffman product. And so you end up just getting a big mess. And it's not very useful. And so in this case, it's essentially no useful reaction that happens here. If the leaving group is on a tertiary carbon, though, in that case, you form a pretty stable carbocation. And since the base and the nucleophile have the same strength, you'll get a mixture. You'll get the E1 reaction happening, and at the same time, you'll get the SN1 reaction happening. And those happen in about a 50-50 mixture. So this table is we're going to use for a long time now. This table is something that you'll want to have in your mind, that you'll want to be able to reference in your mind's eye. We'll use this table to look at our reagents, look at our substrate, and using this table and our knowledge of these mechanisms, we can quickly predict what product we would get. We'll take a big step closer to being that chef magician.